Good morning. My name is Victor Santos. I am a master's student at Universidade Federal of Santa Maria in the CAP group, Quantum Information and Measured Phenomena. And today I'm going to talk about the work I'm developing with my advisor, Janus Mazier, which is called Mapping Prime Numbers Using Entanglement Dynamics. So a brief overview, I'm going to talk about the method I developed to identify primes, and then I'm going to make some application on my spin application, and then talk about the conclusions and further perspectives. So this idea of using physics to take mathematical problems and solve them is not new, and in particular, the identification of primes is of heavy interest because we have classical cryptography, which depends heavily on our capability of breaking the factorization of a general integer into its prime factors. So this is a sketch how this works. So we pick, for example, an integer, then the physicist goes there and chooses a physical system of interest and a quantity Q that he wants to measure. Then he goes there, he measures that quantity, and he knows, he chose the quantity properly, so he knows he can write it as a function of another function, f of n. And this function, after he makes the inversion of inverts the quantity q, he can obtain the function f, and that function will have all the information about the primes that we want. So our idea here is that we apply this not only to a physical system, but a quantum one. And even though I won't be talking about the implementation of this idea here, my master's work is focused on the implementation and this experiment of this method in a quantum computer. But here I'll talk about the theoretical work I've developed. And the idea is pretty simple. So we have a composite system, AB, and this system will evolve to be an entangled system. And after that, we go and we must find some quantity Q to measure. And this quantity, as we'll talk now, is the linear entropy, which is very important. So revisiting the linear entropy is pretty simple, defined as 1 minus the purity, which is the trace of the density operator squared. For a composite system, we don't use the density operator of the whole system. We use just the density operator of one individual subsystem. For example, I have a system AB, so I must take the density operator of this subsystem A or B. The result will be the same as the equations 2 and 3. So, but what does it measure? So linear entropy is useful because, well, when you have a calculation for one system, it is a measure of classical uncertainty. So we have like a machine that shoots the states, and we don't know what states come, but we can assign to it some statistical, some statistical and uncertainty. And in the case of a composite system, we have not measured exactly some classical uncertainty, but a quantum one. In fact, we have, for example, the Bell state, which is very famous in the EPR paradox. So we can see this is maximum. This have maximum superposition, as we have the 50% of getting state 0, 0, and 50% of getting 1, 1. And this superposition translates itself into a quantum correlation, since the collapse of the states on one individual system will collapse the states to the other system. So if you get 0 in one subsystem, we get 0 in the other, and same for 1. If you get 1 in one subsystem, we get 1 in the other. So here's the idea. We first construct the most general Hamiltonian for this kind of composite system, the equation 5. We have the first two terms being the individual parts, and the last part with the coupling constant lambda is the most important, and it's the part that will generate the dynamics for the entropy. So if you restrict ourselves to pure initial states, we can write, for example, equation 6, we can write this initial state in the eigenstates of the individual Hamiltonians. So we have the eigenstates index A, E index B representing the eigenstates of both subsystems. And we have these constants, the C. So we have found that for our method to work, there are some restrictions. The coefficients must be all positive or all negative. It doesn't matter. I chose positive because it's convenient. And the Hamiltonians of both individual subsystems must be constant in time. But the heaviest restriction that we have found is that the energies must be quantized. So they must be linear, dependent on some integer n. And applying these restrictions to the formulas we have introduced for the linear entropy, we reach the equation 10, which is actually pretty simple, but we have this sum that will be interesting for our goal. So when we go and we write we see that there is some complex exponential, and we go and we write the Fourier series for this entropy. We found that the coefficients of the sign must sum up to 0, and the only coefficients are the constants a alpha 0 and the coefficients of cosine alpha n. So we get that formula 13, equation 13, and this is the result that we want, and that it's really important because, as you can see, we have delta, Kronecker delta, and there's some restriction for if we fix some n, there are only some set of values of j, k, l, and m that will satisfy this relation that is expressed in the equation 14. So, as you can see, we are actually decomposing the integer n into a product of two integers, and of course the trivial solution is make one part with equation 15 equal to n and the other part equal to 1, and vice versa. This is a trivial solution. All integers n satisfy this kind of solution. But there are some composite numbers that satisfy extra solutions. So we can see that since all the coefficients are positive, we have some kind of lower bound for primes, which are exactly the numbers that satisfy only that trivial solutions. But for composite numbers, we have extra solutions, which means we have bigger values for the coefficient alpha n. So the physicist goes there, he measures the linear entropy, and then he uses Fourier analysis to calculate this alpha n's coefficients. And since we can have the lower bounds theoretically, he can pretty much tells if that prime he's studying, that integer he's studying is a prime or not, if it belongs to the lower bound or not. If it's above, there is a composite. If it belongs to the lower bound, it is a prime. So here we apply this analysis to a spin system which satisfies all the conditions I mentioned. This is called the spin current state, the equation 17, and we have these two parameters, u and s. S, we want it to be as big as possible, to test bigger integers, but u is some parameter we can adjust as we want to make the performance of the curves better. So we tested here for 3 values of u. and this is logarithm of the alpha n versus the integer n, and we have this the lower bound being the red curve, the other curves being the almost primes, what we call semi-primes, which are integers that are decomposed as the product of only two primes. So we can see that for this particular case, u equals to 1 is the best one, since the logarithms are close to 0. It means the coefficients itself are bigger for this value of u. So we have shown here that within some restrictions, we have a way of telling through a quantum system the primes, if the primality of integers. Of course, there are only some systems that respect the quantized energy condition, but as we analyze in future with quantum correction codes, this method will turn out to be really strong. And there are some details I didn't mention about calculating the alpha n's themselves for bigger n's, which is numerical difficult, but we think, we suspect that this is going to be solvable. And in the this is all theoretical, but in the quantum computer implementation scheme, we did some progress. This is actually as I mentioned, my master's work. There are some details such as estimating the linear entropy, not quite so easy. Also, since we use not only two levels of energy, we use d levels. This translates to using qubits instead of qubits in a quantum computer. This is not quite so easy as well. And the names themselves of such systems not so easy to implement. But we did some developments that I didn't share here. But in that matter, to implement actually this method and test how efficient computationally it is. So here are the main reference I used. Thank you.